Hello, AP Chem students. My name is Lou Akampora, the Science Director for Advanced Kentucky, and a long-time AP Chemistry teacher. And I'd like to talk a little bit about something that's not usually part of the AP Chemistry curriculum traditionally, but has become more and more important, and that is Coulomb's law. And just to kind of motivate some of this, the goal of AP Chemistry is to have you not only describe matter and its interactions, but also to explain them. And it's the Coulomb's law and the forces between the particles that are relevant to chemistry that allows you to do so. So, we're talking about describing and explaining. Historically, and I don't want to turn this into a history lesson, but chemistry really grew as a science when we discovered that, or figured out that most matter is made of small indivisible particles called atoms. And that just really go back to Dalton in about 1810, a little bit more than 200 years ago. And his model of an atom might be just a little blob. And the word atom comes from indivisible. And it was thought that the different elements had their own different kinds of atoms. Things stayed for about 80 years, pretty boring, until Thomson realized that atoms were not so indivisible, and he discovered the first subatomic particles, which he called corpuscles, and we call electrons. And that was about 1900, a little before that. And from there, we've worked out the structure of the atom. And in order for you to explain things like, why is water made up of one oxygen atom and two hydrogen atoms? Why does it have the properties that it does? Why is sodium chloride a white crystalline material? You've really got to know about the structure of the atoms. Thomson had the so-called plum pudding model. Rutherford, his big contribution was to discover the atomic nucleus, that most of the mass and positive charge of the atom is concentrated in the center. And that was the so-called gold foil experiment in all your textbooks. And then Niels Bohr worked out, based on spectroscopic evidence, that the electrons are restricted to only certain allowed energy levels in the atom. And then from there, and that's about 1920, we have a quantum mechanical picture of an atom. And that's due to a lot of people. But this is really where you need to start explaining why and how things happen. Quantum mechanics. Yeah, cool. And we'll talk about that a little bit, but what this has in common is that the atom is made of charged particles. And it's fundamentally important that we understand that the nucleus of the atom is positively charged, that the electrons are negatively charged, and there are forces between these charged particles. And that's where Coulomb's law comes in. So I'm going to erase this very quickly and forget about chemistry for just a minute and talk about charge and Coulomb's law. Coulomb, he predates Dalton, so physicists and natural philosophers knew all about charge well before chemists even knew that atoms existed. And what they had figured out is if you have charged particles, and I will just represent charges by the letter Q, if I've got two charged particles, I'll call them Q1 and Q2, and these particles are separated by a distance d, that there is an electrical force between them that's proportional, or equal to some constant times the product of the charges, so that would be Q1 times Q2, over the square of the distance between them. And this is one way of expressing Coulomb's law. Not particularly the most useful for chemistry, but it's a good place to start. And this tells us that how strongly these two particles are attracted to each other or pushed apart from each other is proportional. And this K is a unit of proportionality to the charges multiplied by each other and divided by the square of the distance between them. This, by the way, is pretty common pattern in some physical laws. You're probably familiar with the gravitational law that Isaac Newton worked out that says that the force of gravity between any two particles with mass is proportional to the product of their masses and inversely proportional to the square of the distance between them. there's the same sort of law that happens with light intensity. And this comes about, a little digression here, because if you think about a particle, think about a light bulb here. Here's a light bulb that's giving off light in all directions. And in 3 dimensions, the light's coming out toward you and going back into the blackboard. Well, if the same amount of light is going through these different surfaces that are different sizes from the light bulb, then since the surface area of these spheres would grow as the square of the distance from the center, if that's d, then the surface area of a sphere, the surface area would be 4 pi times d squared, then it would make sense for the intensity of that light to get weaker as the inverse of that, because the same amount of light would go through the inner sphere or the next sphere. So there's a fundamental reason in nature that many of our laws have this inverse square form. I also want to take a minute to talk about units. This might not seem too important right now, but when you study electrochemistry, you'll need to start measuring charge. But for now, let me refer first to the gravitational law. And most of you may realize that in the metric system, we measure masses in kilograms and distances in meters. And the unit of force you might be a little bit less familiar with, unless you've taken physics. The unit of force is a Newton, which works out to be about 1/5 of a pound. And that means this constant of nature, the gravitational constant, is going to have units of Newton meter squared per kilogram squared. Because when we cancel out everything, almost everything, the kilograms will cancel, and the meters squared will cancel that meters, which would be squared, and we'd be left with newtons and newtons. And the value for G is about 6 times 10 to the negative 11th Newton meter squared per kilogram squared. So if I had a 1 kilogram mass in my left hand and a 1 kilogram mass in my right hand, there'd be a gravitational attraction between them of about 6 times 10 to the negative 11th newtons, which would really be unmeasurable. It'd be very, very difficult, very, very specialized equipment to actually measure that. When you've got something the size of and mass of the Earth or the Sun, then this gravitational force becomes pretty important. Coulomb's law has the same form, and I want to talk about the units here as well. Forces are still measured in newtons or expressed in newtons. Distances are still going to be expressed in meters. But now the unit of charge you might be a little bit less familiar with. You probably know that the electron, we talk about having a charge of -1, and a proton has a charge of +1, but there is actually a unit of charge that's going to become important. And if we were to charge something up, we want to measure how much charge is on there. The unit of charge might not surprise you, but it's called a Coulomb, with a capital C. And if I have 2 charges, I get C there, C times C. And that means the unit of my electrostatic constant will be Newton meter squared per Coulomb squared. And a Coulomb is actually a large amount of charge. The numerical value for K is going to be roughly 9 times 10 to the 9th, or 9 billion. That's about 2 billion pounds. So if I had a 1 Coulomb charge in my left hand and a 1 Coulomb charge in my right hand, there'd be about a 2 billion pound force between them. Obviously, I'm not quite strong enough to hold them apart or pull them together. The one big difference, and most of you probably know this, between the electrical force and the gravitational force is that masses are always positive. Even if you've got antimatter, the masses are always positive. Charges can be either positive or negative, and like charges, 2 positive charges or 2 negative charges will repel each other or push each other apart, and opposite charges will attract each other. So in this case, even though these are huge forces, because most matter is electrically neutral, most matter is made up of the same amount of positive and negative charge, we're usually pretty unaware of this electrostatic force. We can do special things to apply or separate charge, and we'll talk about that briefly. But on a walking around level, most of us are pretty unaware of the electrostatic force, certainly compared to the gravitational force, which is keeping you in your seats, a certain amount of politeness and maybe some interest. But when we get down to the atomic level, where we're talking about atoms and ions, Coulomb's law becomes very, very important. So let me just take a break here and come back in a minute and talk about something else.